All right, so next one, just continuing on in chapter 3, balancing equations. So I'm looking at this reaction here. There is a little bit of luck and trial and error in how you do these things. So when I look at this reaction, it's a pretty simple reaction, but it does demonstrate that the luck involved. If I decide when I'm looking at this reaction to start out looking at chlorine, then it's going to actually lead me to kind of a dead end, or I'm going to have to do some manipulation to figure it out, because with chlorine, I look at 2 here and 3 here. I'd want to go to the lowest common multiple, which would be 6. So I'd put 3 Cl2s and 2 PCl3s, but then that's going to kind of mess me up when I look at phosphorus. So seeing that, I would probably erase my coefficients and start over. And then I would say, okay, let's look at phosphorus first. I have 4 phosphorus atoms here, I only have 1 here. So if I put a 4 in front right here, that's going to balance phosphorus. But if there's a 4 here, 4 times 3 gives me 12 chlorines. So that means I'm going to need 6 Cl2s. So my balanced equation should be 1 of these, 6 of these, 4 of these. And it works. Again, you could have gotten there from chlorine also, but it's a little bit harder that way. That's just the luck of the draw. So when you balance an equation, if you do get to a point where you're a little confused, start over, pick a different element to focus on, and work from there. All right, last one. Look at this one. Again, if I'm looking at everything, I might just notice right off there's 2 chlorines right here. So I'm going to put a 2 in front of KCl. And then if I have 2 potassiums, I'm going to put a 2 in front right there. And then honestly, if you look at everything else, I'm done. All right, so now we get into some harder ones where I'm like the previous slide, I kind of gave you the formulas and had everything set up and you just had to balance it. There are going to be times also where we have to come up with the reaction ourselves. So the first one here, formation of liquid water from the elements. So I kind of have to think about what does that mean. So the formation of liquid water. So that's implying that water is going to be the product of the reaction. So I'm going to put water on the right side of the reaction. It specifically said liquid water. So I'm going to put a subscript with the L in it for the liquid water. And then it said formation of water from the elements. So I'm starting out with the elements, putting them together to make the compound. So what elements do I need? Well, obviously I need hydrogen. And I need oxygen. So if I look at that, that's really ugly to a chemist, because I'm supposed to also remember hydrogen and oxygen are both on the list of diatomic elements that we learned. So anytime hydrogen by itself, it's always going to pair up as H2. Anytime oxygen's by itself, it's going to pair up and be O2. Okay, so that's the proper chemical form. And then hydrogen and oxygen, when they're pure elements, they're both gases. So I should put gaseous hydrogen and gaseous oxygen. So now I have all the formulas written correctly. So then I have to balance the equation. So if I ask you to balance the equation, normally in this chapter, I always want whole numbers. So I would look at this and say, well, I've got 2 oxygens here. I only have 1 oxygen here. So I need to do a 2 here. And then 4 hydrogens. So I need to put a 2 here. Okay, that's the equation I would want to see. I will say there are going to be cases where if you write the reaction for the formation of water, and when we get to chapter 5, when we're doing thermochemistry and stuff, it'll give you the amount of heat involved in making a mole of water and all that kind of stuff. That would be a case where you're going to occasionally see a reaction that actually has a fraction in it. So I can write the same reaction but if I want to make 1 mole of the product, if I lock this in as a 1 right here, then that means I'm going to need a 1 in front of hydrogen, which is fine. But to get 1 oxygen atom, that's only going to be half of NO2. Okay, so that equation, while correct, is not really how we prefer you to write the reaction in this chapter. In this chapter, if I tell you to balance the equation, I want whole numbers. But be aware that later on there are going to be special cases where they want to lock in 1 mole right here. Specifically in lab, you're going to do an experiment. Actually, no. If you're on campus for lab in future semesters, Hess's law is a reaction, an experiment where you have to write reactions to have a 1 on the product side. Okay? Again, special case, don't worry about it right now, but just be aware that if you ever see it, it's not that it's wrong, it's just not the best way to do it. It's not our preferred method. All right, so then the next one, again, it's not showing very well on the PowerPoint because of my board, but I give you a reaction in words, and you need to be able to come up with the whole reaction on your own. Okay, so I'll read off. The statement in the PowerPoint says, a pinch of sodium carbonate reacts with nitric acid solution to yield water, carbon dioxide, and sodium nitrate. Write the balanced equation. So we're going to go through it piece by piece. It says sodium carbonate first. So sodium is Na, carbonate is CO3. But you have to think about, and this is where it's easy to get messed up, this is an ionic compound, metal, non-metal ion, okay? It's an ionic compound. I have to think about charges to make sure I put them together in the right ratio. Sodium's a group 1 metal, so its charge is +1. Carbonate, you're supposed to memorize, is -2. So therefore, swap your charges. This should be Na2CO3. And it said in the sentence, a pinch of sodium carbonate. Ionic compounds are solids under normal conditions. Okay, so it reacts with nitric acid solution. So when at the end of chapter 2, I mentioned that there are a few acids that I expect you to know: hydrochloric, nitric, sulfuric, phosphoric, and acetic. Those are the 5 I want you to know. All right. So nitric acid is one of those. You're supposed to know that it's HNO3. Okay? And if it says the word solution, that implies that you've mixed this compound in water most of the time. You can use other solvents every once in a while, but again, in this class, if we ever talk about solutions, we're going to assume that they're aqueous solutions, which means everything's dissolved in water. Okay, so this is going to be AQ, stands for aqueous. So we mix those together, they react, and then it forms. It says to yield or to form water, H2O, liquid, carbon dioxide, CO2 gas, and sodium nitrate. I'm just going to drop down. It all should be on the same row. Na is sodium. NO3 is nitrate. And then sodium is +1. Nitrate is -1. So they go together 1 to 1. That's the correct formula. And then one thing that's not in the sentence, sodium nitrate, if I form this ionic compound, most ionic compounds are soluble in water. So this, like the nitric acid was dissolved in water, when I would probably pour it into a beaker that had this compound, or I'd add a squirt from a pipette or something. But there's water present. So when I form this ionic compound, most ionic compounds are soluble, but not all of them. In chapter 4, you're going to have to learn the solubility rules so you know which ones are soluble and which ones aren't. For now, I'm just going to tell you this is a soluble compound, so it's going to end up being aqueous because the reaction is happening in water. Okay, so what I would notice is when I mix these together, the solid would dissolve in as it reacts. I'm going to have bubbles of CO2 gas coming out, and then the solid will disappear because everything else is going to be in the solution. All right, so that gets us through balancing equations. So now we get back into more of the math side of everything, where like we know what reactions are, chemical equations, we know how to balance them. Now we need to introduce a new topic called the mole, and then after a while, probably 3 or 4 videos from now, we'll get back to the reactions and moles and put it all together. Okay, so what is a mole? If you picture a furry little creature like that, it's really cute. That's not it. That is not a mole when we are in chemistry. A mole is just a number. 6.02 times 10 to the 23rd. We refer to that as Avogadro's number. Sometimes students call it avocado's number. But it's just a number. It's kind of like if the word dozen. If I say, hey, go get me a dozen donuts, everybody would know that means 12 donuts. If I say, go get me a dozen eggs, you'd go get me 12 eggs. If I say, there's a dozen people in the room, you know that that means 12 people, right? So the word dozen, we have accepted that that word represents a number, okay? In a similar way, the word mole in chemistry represents a number, 6.02 times 10 to the 23rd of anything. So if I say, go get me a mole of donuts, that would mean go get me 6.02 times 10 to the 23rd donuts. If I said, go get me a mole of eggs, that would mean go get me 6.02 times 10 to the 23rd eggs, right? There are a lot of words that we use that represent numbers. If I say, go get me a pair of socks, you know that means 2 socks. If I say, go get me a ream of paper, standard paper, that's supposed to be 500 sheets of paper, right? So there are just certain words that we know represent a number. So mole needs to become part of your vocabulary. That number, you need to remember it. It's going to come up a lot. So what does it mean and where does it come from? Well, basically, if I had exactly 12 grams of carbon, specifically one isotope, carbon 12, then it's the number of carbon atoms in that sample. Like that's the pure definition of what a mole is. It's the number of carbon 12 atoms in 12 grams of carbon. And I mentioned before with atomic masses and stuff, carbon 12 is a reference that's used for a lot of other things. So that number 6.02 times 10 to the 23rd, essentially what it really is, Avogadro's number, which is that number, it's the conversion unit between AMUs and grams. Okay, and what that means, kind of like the conversion unit between inches and feet, there's 12 inches in a foot, so 12 is like the magic number between those two units. Avogadro's number is the magic number between AMUs and grams. If I want to know like how many atomic mass units are like one atom, each proton and neutron weighs about 1 AMU. So the weight of an atom is going to be a number of AMUs. If I want to take AMUs and convert into grams, which is a much bigger unit, that's the number that relates them. Okay, now on the previous slide I think it said 6.02. Here it says 6.022. I mean, you can get Avogadro's number to more sig figs, okay? It just depends on how particular you need to be. But the key information that we need, 1 mole of an element, which we already said, 1 mole means 6.02 times 10 to the 23rd of that element, okay, of the atoms or molecules or whatever. So 1 mole of something is going to have a weight equal to its atomic weight in grams. Now what that means is 1 carbon 12 atom weighs 12 AMUs. A mole of carbon 12 will weigh 12 grams. By switching from AMUs to grams, it's going to, I know that I have 6.02 times 10 to the 23rd atoms of carbon weighs 12 grams. It allows me to take the weight of 1 atom and apply it to a much larger sample. So it makes it a very useful value. Now, why is that important? Well, if we go to lab and I say, hey, go get some water out of the sink or something, you can't get 1 water molecule. You can't get 10 water molecules. It's impossible. You can't get such a small sample. We can't in lab work with individual atoms and molecules. It doesn't work. They're too small. We always have to up the scale to a higher value where I could say, go get a beaker of water. Okay, the molecular weight of water is 18 AMUs, right? So 1 water molecule weighs 18 AMUs. I can't tell you to go get 18 AMUs of water because it's too tiny. We can't even see it, okay? But I could tell you to go get 18 grams of water. 18 grams of water is 18 milliliters because the density is 1 for water. So that's a usable amount in lab. But if it were 18 grams, like, well, okay, but how much water is in there? Well, this relationship from AMUs to grams tells me that if you get 18 grams of water, which is the molecular weight of water, then I know that there's 6.02 times 10 to the 23rd water molecules in there. So it's a connection that allows me to go from individual molecules to big, large samples, and I still know how many molecules are in the sample. 1 mole is the molecular weight in grams. So it's a quick connection. The molecular weight of a compound, which technically should be in AMUs, like the molecular weight of water is 18 AMUs, is going to be the same number as what we call the molar mass. It's the mass of 1 mole. 1 water molecule weighs 18 AMUs. A mole of water would weigh 18 grams. It's the same number, but a much bigger unit. All right, and then finally, when we look at the periodic table, the units, if I say what's the molar mass of something, for water, we just said the molar mass, 18 grams is what 1 mole weighs. So the units we use are called grams per mole. The molar mass of water is 18 grams per mole. Okay? The molar mass for carbon dioxide. Well, carbon weighs 12, oxygen weighs 16, so CO2, the molecular weight, 12 plus 16 times 2, will be 44 AMUs. So the molar mass will be 44 grams per mole. Okay, so we got to be able to do that quickly and efficiently. Remember what I said, we prefer to use whole numbers for our weights if they're really close to the whole number. If it's not close to the whole number, then you want to keep 1 decimal place. That's how we add up our molecular weights. I'm going to have to cut the video off and we'll do another one.